Hello, we are here for one more lesson of this AxisVM training course. And the topic for today will be the static analysis. We are entering a new chapter where we will see a little about different types of analysis. And this is important to mention because AxisVM lets you perform linear and nonlinear static, linear and nonlinear dynamic, vibrations, and buckling analysis. And we'll try to speak a little about all these topics. There are common steps when we talk about all these types of analysis. So each analysis consists of the same steps. First, model optimization. Second, model verification. Third, performing the analysis. And fourth, results file generation. Starting today with the static analysis. It's not the analysis itself, the calculation, because we have examples also how to do this in particular, but to speak a little about the parameters involved in both of these analyses, the statics, linear and non-linear. So I've opened one very easy example, and particularly we are talking about this icon here, static, which opens this diagram, this toolbar, where we have in here the linear static analysis and in here the non-linear static analysis. First, to mention that the term static means that the load does not vary with time. So this is linear. And when we go to linear, we get immediately about the load cases that are applied. So we can start the analysis. So the analysis, it is done according to what was defined. It's not very important, particularly what is defined, because we've seen already a couple of different topics and lessons about the load cases and so on and what to apply. It is important to mention where to perform and what is behind. So in here we've executed a linear static analysis, and when we mean linear, means that the computed response, and when we talk this we are thinking about displacements and internal forces, is linearly related to the applied loads, loads. All the load cases are solved with this analysis, and through the geometric linearity, it is assumed that the displacements remain within the limits of the small displacement theory. This means that we are working on an area that is called linear elastic area. So this is where we play when we work with linear analysis. On the other hand, we have the nonlinear analysis, which it's accessed when we go to this button here. We get this dialog box where we can set some parameters to apply this analysis and to define what we want. And the term nonlinear means again that the computed response, so again the displacements and the internal forces, is non-linearly related to the applied load. This can be due to the use of gaps, links, or nonlinear supports, truss or spring elements, or taking into account the geometric non-linearity of the truss, beams, ribs, and shell elements. And we can choose the load cases from this area here where we see everything that is defined. and then the system will calculate this nonlinear analysis to what is chosen. Some parameters that we must understand before execute the calculation. First, solution control. It can be set to force or displacement. When it is set to force, the increments are applied as fractions of the loads. And when it is set to displacements, the increments are applied as fractions of the displacement component of the node specified. Okay, it's a little different. We have another function, the pushover, which, as the name says, it's more focused for the pushover analysis. This control, it's a special type of displacement control that allows the use of a constant load case while having another parametric load case that it is increased incrementally. This is essential for the pushover analysis, and in this particular case it's not on because I'm not doing a pushover analysis. Then we have a couple of things like this tracked mode, which we can set on or not. I'll go back because I don't want to leave this dialog box. So we can set a couple of things, direction and maximum displacements. So in the case of a displacement or pushover control, we can set the degrees of freedom. We can set the direction and the maximum displacement allowed under the direction that is chosen. So a couple of possibilities that we can control to make the analysis. Then load factor. This load factor can be used to multiply loads on the selected load case or combination for this type of analysis. So number of increments, we can have these equal increments and we can set the number of increments. Basically we have these two methods, either equal increments or increment function. So equal increments, we can specify the number of increments. We have a default like this one that is 10. When we have a highly nonlinear behavior analyzed, we can specify a greater value to achieve convergence. With increment function, we can loads are not increasing in a linear way, but follow a predefined function. So when we use this increment function, it is possible to reduce the number of increments where the behavior of the structure is linear and increase the number of increments where the behavior is nonlinear. There is one important topic about this, which is this increment function must be monotonous, or saying it on the other words, loads cannot decrease. Then we have another group called convergence criteria. And based on the convergence tolerances you specify, AxisVM will determine if this nonlinear solution reach the required accuracy, which we call here the convergence. So we can set a maximum number of iterations, and this is specific for each model. We can, if we have a greater number of iterations, it will take more time, but in the end may allow you to reach what we want. Then we can use which is the criteria, if it is for displacement, for force, or work, or all. and we have the tolerances, and these interactions will try to find a solution under what is defined inside. Then we can have also another option for use second stiffness only for appropriate cases, as the name says. And if this option is selected, then the beam end releases are represented by their second stiffness instead of a tangent stiffness. This improves the convergence, but slows down a lot the calculation. So it is recommended only if we cannot reach the convergence, and we need to increase the number of iterations and have this set on. Another group of things, which in this particular case it's not highlighted. In here we can use reinforcements in calculations if we activate this option that I cannot reach now. This is especially useful when we are analyzing reinforced concrete plates. We can have taken into account the calculated or the actual reinforcements. Okay, so we can set these functions on. And we can have in considerations also this creep and shrinkage with or without. So a couple of options also to consider. Finally, the nonlinearity, we can have two choices. We can choose this one, follow geometric nonlinearity of beams, trusses, ribs, and shells, or follow nonlinear behavior of materials and finite elements. It depends of what we have on the model, so I have only one option in this particular case. If we set this first option on, if the model contains elements with nonlinear behavior, or elements with nonlinear material characteristics, it is used this function. If the equilibrium is established in respect to the deformed line elements, we use this option here, and we have to consider also the type of elements we have on the calculation itself. So, but these are some a little more detailed ideas how to use each one of these cases. So this was what I had to show you about this first analysis, calculation, and in particular it was this the static ones, either linear on and non-linear. You can check also some examples we have for this type of calculations, and for sure any help that you may need about this topic, you can send us some comments that we will give you all the necessary support.